Thanks for the introduction. Thanks for the invitation to be here. To talk about my work. It seems like a very nice meeting already. I already have very interesting conversations with people. Um, yeah, forward to the rest of it. Well, yeah, I said in my abstract, I'm going to tell you about different types of optimal spectral gaps for different objects. Irregular graphs, unitary representations, and hyperbolic surfaces. I could do that in any order, but I'll start with like things that look most similar to what we saw earlier today. So that's hyperbolic surfaces in their spectral theory. So let me tell you what that is. So H2 is the two-dimensional hyperbolic upper half plane. It's a half plane with a metric of constant negative curvature times 1. So it has an isometry group, PSL2R. So PSL2R acts on H2 by isometries. This is a hyperbolic upper half plane. What you can do with this is you can take a discrete group of this and quotient H2 by that discrete group. Let gamma be a discrete torsion-free subgroup of PSL2R. Discrete and torsion-free. And let X the quotient of H2 by gamma. You get a surface. It gets the same local metric as the one on H2. So this is a surface of constant curvature minus 1. So this is basically my definition of a connected hyperbolic surface. You can take this as a definition of what is a hyperbolic surface. This kind of quotient. If you want to have a disconnected one, you take a union of those. Okay, so this is a Riemannian surface that has a metric and therefore has a Laplace-Beltrami operator. X is the Laplacian in the surface. What do I want to say about it? It's an unbounded self-adjoint operator. On L pseudo X.
Excuse me. Would you recall us what is called torsion free?
Oh, you don't want to have you don't want to have an element like the cube's identity, because it'll give you a point on your surface, which is not like a manifold, it's quotient by rotation of order 3. I could have torsion and I could still do most of the same things, but I just want it to be an honest to goodness surface. Okay, well, the simplest example of the surface is where gamma is just a group with one element in it, the identity. Then my hyperbolic surface is H2 itself. So what does the spectrum for the Laplacian H2 look like? It's a non-negative operator, so it sources here. So this spectrum is absolutely continuous between 1/4 and infinity. This wavy line is my cartoon for absolutely continuous spectrum. The actual pattern of the wave doesn't mean anything. Okay. So this is the simplest thing. This is absolutely continuous spectrum. Yeah, I could tell you everything about it if I get to look in the book. Okay. Okay, what's the next best case? Well, next case is whenever X is a closed surface. So it's closed up. It's a torus with at least it's a genus at least 2 surface. It's the surface of a donut with at least 2 holes. Then what does the spectrum look like? I mean, everyone here knows. You have a compact resolvent, and therefore you have a discrete spectrum. In this case, being closed means that you have finite area, and therefore the constant functions in L2. So you have 0 as a eigenvalue, and then you have infinitely many discrete eigenvalues. But there is an issue, an interesting issue. Okay, so there are infinitely many, and I tend to infinity, as I tend to infinity. So there are infinitely many. But the interesting issue is whether there could be any eigenvalues below 1/4, the bottom of the spectrum of the universal cover. So that's essentially the topic today, about these eigenvalues below the bottom of the spectrum of the universal cover. So I put question marks beside those. And then let me tell you one slightly more complicated setting, which is the case where X is not closed, yet has finite area. Which means that X has some number of cusps that go off to infinity that have finite area but are infinite in extent. And now, in this case, we have scattering theory. What it looks like, well, we're finite area, so we still have 0. In this case, scattering theory gives us absolutely continuous spectrum between order infinity again. It's the same cartoon. Then, same issue as before. We a priori, whatever happens here is qualitatively the same as in the compact case. What can happen between 0 and 1/4 is that there can be at most finitely many discrete eigenvalues. Okay. Okay. So that's there could be no accumulation points of eigenvalues in here. But again, it's a little bit mysterious whether they can actually occur below 1/4. And then there's another thing that could happen, which is really, really mysterious, which is that there could be embedded eigenvalues. But these do not always exist, conjecturally. Lambda 3, 4, and so on. So there are examples of choices of gamma that lead to this picture, where there are provably infinitely many embedded eigenvalues in the continuous spectrum, and they have a Weyl law. Conjecturally, generic gamma in this setting, there should not be there should only be finitely many of these, and in fact there should really not be any. These should not exist.
Some arithmetic meaning? What is their meaning?
Yeah, in some sense. I mean, the proof that they exist uses okay, in the sense that every gamma that's known to give rise to infinitely many embedded eigenvalues comes from number theory. Arithmetic gamma. These are the ones for which they'll self-prove there's a Weyl law. So yeah, in this sense, they're arithmetic objects. So yeah, so the amusing thing about this picture is that every eigenvalue has a question mark. In fact, it's an open question whether there's a finite area non-compact hyperbolic surface which only has 0 as an eigenvalue. Embarrassed. That's actually probably the generic case. So yeah, I said I'm going to talk about spectral gaps. There are a number of different spectral gaps in my picture, right? There's one. There's one here, I guess, as well. I could even ask about this one, even though there's absolutely. But the one I really care about is the one at 0. So this is my spectral gap here. One I care about. From 0 until the next point of the spectrum. Okay. Maybe this is more geometric than most people here are used to. So let me just say a word about why it's interesting to study these spectral problems. Why is it interesting? This Laplacian is quantization of the geodesic flow. It's interesting because the geodesic flow is a no-solve. Okay, at least in the compact case. No-solve, which is a robust source of chaos. So you're quantizing something which is chaotic. Okay, but we know about that. It's easy to do this. So we have quantum chaos. But okay, so we could do something like that where we take like convex bodies in Euclidean space and we do scattering, then we have chaos. But this is much harder. The nice thing about this setting is like you have something chaotic, but there's a lot of structure in the background coming from the fact that hyperbolic plane is PSO2R mods SO2, and so there's a lot of extra algebraic structure. Comes in the form of representation theory. The representation theory of SO2R is in the background. It's just motivational, it has nothing to do with the rest of the talk. All right, so I'm interested in this spectral gap, which is either going to be lambda 1, or if there is no lambda 1, and you're in this case, 1/4. So what, okay, and there's many reasons for which you want to have a large spectral gap. If you have a large spectral gap, it tells you that your surface is highly connected. It tells you that the geodesic flow is fast mixing, so on and so forth. So we want to have a large spectral gap, but there's a priori limit on how big it can be. Of course, in this case, the spectral gap cannot be bigger than 1/4. And the same is true in the compact case also asymptotically. So this is theorem. This is by Hoover. As if you have a sequence of closed hyperbolic surfaces, genus xi tending to infinity. So the genus is the number of holes in the donut. Genus of xi tending to infinity, then you cannot consistently have spectral gap larger than 1/4 by a consistent margin. Then sub lambda 1 of xi. So 1/4 is the asymptotically optimal spectral gap. It's the genus. Okay, there's lots of this story that I'm passing over. Like there's a rich history of studying spectral gap of hyperbolic surfaces coming from number theory that I'm not talking about. Let's just take this as a starting point that says there's a limit on what you can achieve with a spectral gap, and let's ask if it can be saturated. Okay, so that was the conjecture of Boozer from 1984. He said there exists a sequence xi closed hyperbolic surfaces with genus tending to infinity and lambda 1 tending to 1/4. The hard part of this is the lim inf. Lim sub comes from here. And we now know this is true. It's proved. In 2023, I Hyde and myself in 2 steps. So tell you about. First one is this theorem. Starts in a peculiar way. Let X be a non-compact hyperbolic surface. What I'm going to do is I'm going to take a covering space of X of finite degree n. Let Xn be a covering space of degree n of X, chosen uniformly amongst all such covering spaces. So randomly, we're choosing it randomly, and we're choosing every covering space with the same probability. Chosen uniformly with respect to all such covering spaces.
Given an n, how many covering spaces do?
Yeah, I can tell you in this case. So X is finite area non-compact. Its fundamental group is free. So there's a correspondence between covering spaces of degree n and homomorphisms from the fundamental group to a permutation group Sn. We're going to talk about this later. Because you have a free group, a homomorphism from a free group is you just pick an element of your target for every generator. So, okay, you can do the exercise.
Yeah.
It's the size of SMs at some power. If X is a closed surface, the answer is a little bit more interesting. I haven't told you the conclusion. Okay, then these guys have the same spectrum in a large region. Spectrum of Laplacian X in 1/4 minus small o1 0. And this happens with high probability. With probability tending to 1 as n tends to infinity. Okay, so what you want to do with this is you want to choose your original X so that this is only 0. It has no eigenvalues below 1/4. And you only get 0 here, and you only get 0 here, which is what you want. Okay, and then you let n go to infinity. Now, that's not the answer because Boozer's conjecture is about closed surfaces and they're not closed. So you have to have some way of closing them. So that's the first step.
Did you explain what it means chosen uniformly?
I mean, there are finitely many of a given degree. So we choose them all with the same probability. Right? I'm talking about the uniform probability measure on a finite set. So yeah, so there's one probability measure for every degree n. For every degree n, there are finitely many covering spaces of degree n. And we can put a probability measure on that where every single guy has the same probability. Use that probability measure.
Where did the non-compactness play a role in this?
It plays a role in the input I need, which I'm going to explain. So at the point at which we prove this, the input I need I need to the proof only existed for free groups at that point. So I choose a non-compact surface, so I have a free fundamental group. I'm going to explain this. But it caused a problem because I haven't actually solved the problem. I haven't solved the original problem, right? So now to solve the original problem, we have to add a compactification procedure. So this is there are different ways to do this, but the one we use is due to Boozer, Berger, and Dossuk. And what it does is you make sure you have an even number of cusps. So here's a cusp, which is infinite in extent. Here's another. Make sure you have an even number. Pair them up. This is really each of these guys is infinite. Okay, so I'm joining two infinite guys together at their ends, and then replacing this by some finite guy who has a geodesic waist, but this is small. Or in the other direction, this guy is degenerating down to 0, and these guys are getting infinitely stretched out. So Boozer, Berger, and Dossuk prove that you can do this and make the loss that you take in the spectral gap as small as you want. So that's the first way this problem was solved. So that's like history, bringing us up to date. Okay, so yeah, so everything I told you has We're going on to the next. Any questions?
You were saying that at that point, the tools that you had
Right.
were only for the free groups. If you were to prove that theorem today rather than 2 years ago, are there now tools to go directly
Yeah,
instead of
there's a different proof, but establishing the input. Okay, so that's the subject of the talk. I'm going to explain. So yeah, so this is something that happened like 2 years ago, and then I'm going to explain what happened in between, what's happened up to now. Okay. I mean, it's an open problem. Like you prove it however you can, and then afterwards you think, what was it? Well, how should I prove it? Okay. So let's now go to something more basic, which is deregular graphs on a finite number of vertices. Everything I talked about most things I talked about have an analog there. There are some strange omissions. I'm also what I'm doing now is I'm going to talk about how we prove this, but in a sort of roundabout way. The next chapter is analogs or deregular graphs. let's call it G, on n vertices. What's the analog of the Laplacian? Well, you can write down the Laplacian of G, that's fine. But I actually prefer to work with the adjacency matrix. So let's say it's D minus AG, where this is the adjacency matrix. Are these concepts okay to everyone, or should I say more? You have a graph on n vertices, it's deregular, it has an adjacency matrix. The rows and columns are indexed by the vertices, and there's a 1 in the ijth entry for every edge between I and j. So there may be more than one number of edges between I and j. And this is just some kind of normalization or shifting that I prefer. So I prefer to work with this guy. It's an n by n matrix. It's real and symmetric, and therefore it has n eigenvalues beginning at d, which is lambda 0, and the 1. These are the eigenvalues of the adjacency matrix. And to lambda n minus 1. What's the analog of the fact that lambda 1 is 1/4 plus small o of 1 as g tends to infinity? This is an older result due to Alon and Bopana. And there's a funny thing about deregular graphs or finite graphs, which is not true for hyperbolic surfaces, is what the spectrum has two sides, right? The spectrum here only has one side. So you can always choose to do things from both sides or from one side. I'll just do the two-sided way today, which involves me making the definition that lambda 1 star is the max of either lambda 1 or the absolute value of lambda n minus 1. Okay, so this is the replacement of lambda 1 if you want to control both sides at once. And the analog of this is that this is at least 2 root d minus 1 minus small o1 as n tends to infinity. This is a very famous bounding spectral graph theory called the Alon-Bopana bound. This is the spectral radius of a deregular tree. What's next? Okay, theorem 2. Did I call it theorem 2? Yeah, I did. Okay. What's the analog of theorem 2? Well, I'll just do a special case. If your graph G is the wedge of D circles here, and you take a unit and you take a covering space of this, that's just what a deregular graph is. In fact, so let's say it's actually R of these and B is 2R. Right. Then this analog of theorem 2 in this case is quite a famous theorem called Friedmann's theorem, which we're going to spend some time on in a second. Friedmann's theorem says, in informal language, almost all deregular graphs have almost optimal spectral gaps. Now let's do one in the other direction. So here's something here. There exist Ramanujan graphs. With n unbounded. What does Ramanujan mean? Ramanujan means you have the optimal spectral gap, but you have this 2 root d minus 1 exactly. So lambda 1 star is less than or equal to 2 root d minus 1. And the funny thing about this is that this is open on this side. So the original construction of Ramanujan graphs is due to Lebotsky, Phillips, and Sarnak, and independently Margulis in the 80s. There was a more recent construction of one-sided Ramanujan graphs due to Marcus Spielmann and Srivastava in 2014. Yeah, we don't have any analog of this fact for hyperbolic surfaces. It's one of the main open problems. Does there exist a sequence of closed hyperbolic surfaces with genus tending to infinity and lambda 1 greater than or equal to 1/4? Yeah, so that's very nice. Like, there's a dictionary. Can you actually make, can you make this dictionary give you mathematical implications, like from one side to the other? And the answer is like yes, and we also understood that for a long time. Let's just use this. So there is actually a principle by which you can transfer spectral gap from graph to a manifold if the manifold if the manifold has the structure of the graph. Let me just explain a little bit about that. Just okay, so what do I want to say? So the random cover xn, let's think about it for a minute. So we're going back to theorem 2. If okay, so what do I want to say about this? So the point is this random cover has the structure of a d-regular graph. And I want to explain why. So I have my gamma acting on H2. I don't know if everyone knows hyperbolic geometry, but what I can choose for this action, this group action, is a nice fundamental domain. Okay, so it'll be some finite area non-compact piece of the hyperbolic plane. This is the fundamental domain. So H2 is tiled by gamma translates of this guy, and my x is obtained by gluing some of the sides of this guy together. Okay. So that's for x. If I have a degree n covering space, I can lift this tiling from a one tiling of x to an n tiling of xn. So now there'll be more than one, there'll be n tiles. The tiles will meet along some faces. So this is like, I've just drawn 2. What I can do is I can put a vertex in each of those tiles and join them when they meet along an edge. Okay, so this will define a d-regular graph for some d. Okay, and so I really have a family. You know, everything's asymptotic. I have a family of d-regular graphs and I have a family of covering spaces. And there is a principle by which you can, going back to
D here is n or
yeah, so d here will be 2 times d here will be half the number of faces. The fundamental, I mean, I haven't told you exactly how I glued these guys, right? There are 2 choices: 3 times punctured sphere or once punctured torus. Both cases, the fundamental group is F2, free group of rank 2. So then D will be 4, actually. Yeah, it's actually the number. So like we can see actually 1, 2, 3, 4. Going back to the thesis of Mark Berger. Sentence has the structure of a d-regular graph on n vertices. Going back to Mark Berger's thesis, we can transfer the spectral gap. So if we know that the family of graphs have a uniform spectral gap, we deduce that the family of hyperbolic surfaces have uniform spectral gap. But that's really inefficient. This is inefficient. So you lose a lot of constants when you do this. This is inefficient. Inefficient. So what I'm going to say, someone can probably disprove in some example, but you can never produce asymptotically optimal spectral gaps like that. You take too much of a loss. It's too inexact. So what I'm kind of claiming is that you couldn't just use Friedman's theorem that you're almost always getting the optimal spectral gap for the graph, and then just run Berger's thesis and get the almost optimal spectral gap for the surface. You have to do something more. You have to ask for something more than expansion. You have to ask for more than the spectral gap. GM. More than the spectral gap. Yeah. I'm going to tell you what you have to ask. I'm not sure if what I'm saying is provable, but we don't know how to do it like that. So what it works is we ask for more. Right. So now what I'm going to do is go back and state this theorem in a precise way. So Here's Friedman's theorem. I'm gonna do it when D is 2R. Like, any more questions?
You already mentioned this, that how is this D? So you have a manifold and you
Yeah.
have a graph.
Yeah.
What is the number D that you?
Yeah. D is the number of faces of the fundamental domain for the
It
manifold.
can be any number.
Yeah, it could be anything. I mean, in this case, it can be. It has to be at least 4. It's also twice the rank of the fundamental group. That's why I'm saying it can't be 2, because cannot have a finite area hyperbolic surface with fundamental group Z.
So this inefficiency in the in running this argument, what does it give in the first place? Like, can you get at least some result? That's
Right, so yeah, you get uniforms, but you get the uniform random covers have a uniform spectral gap for some constant.
but like, is it epsilon or is it like 1/8?
No, the annoying thing about it is it heavily depends on the geometry here. I can like run the argument really quickly, right? So like I have something low energy, so we use energy estimates. Something. So this is all low energy stuff, right? Except if you want to work down near 0, then it's all really low energy stuff. If you want to go the whole way up to 1/4, then you start to go close to the edge of the continuous spectrum, so you have to be careful.
Yeah.
So let's just do really low energy. So you have some eigenfunction, primitive eigenfunction with really low energy. So you use energy estimates, like the energy small, you break the energy integral up onto the tiles. So the energy integral is small on most of the tiles. I'm not being precise about what London is. And then use the fact that the energy integral on a tile with no boundary conditions is controlled by Neumann. So you have something, you have to deal with the Neumann eigenvalues, but use the Neumann spectral gap. It tells you for the tile, it tells you that if something has low energy, it has to be almost constant. So like, roughly speaking, the eigenfunction is roughly constant on each tile. And then you run the same argument for all pairs of tiles, double counting. So you get that the eigenfunction has to be constant here and constant here, but also constant on 2 adjacent tiles, and therefore the same. Okay, this is it. Like, you can do it yourself. So, but like, it involves knowing the Neumann spectral gaps, and so it depends on knowing the geometry of the tiles. And like, this result is up to the spectrum of the base, which you can never get rid of, is agnostic of the.
Given a manifold X, how much freedom we have for the fundamental domain? Is it essentially unique, or?
No, it's definitely not unique. You can make it really bad if you want, where it's like got all sorts of horrible boundary but in the case of hyperbolic geometry, you have some nice things where things called Dirichlet fundamental functions, where you pick a point and you look at its orbit onto the group, and you look at all the bisectors, and then you learn that there's some bisectors that bound some.
So there are some distinguished.
There are some distinguished fundamental domains called Dirichlet fundamental domains for. Yeah, I mean, so this is not. I cannot generalize this very much. I cannot do this in variable negative curvature, for example. Berger's thesis is very general. It works for like, I think it worked for any manifold. I didn't read it. It's not easy to get, but yeah.
For Brooks as well, where he does it.
Yeah. Any other questions? Right. Okay. So let's state a version of Friedman's theorem. So let's pick some random permutations. Sigma 1, sigma r, be elements of the permutation group on n letters. This is Sn permutations. These are IID. and uniform, like before. So uniform all it means, like, if you have a finite set, choose everything with the same probability. Okay. Okay, and then x1, the xr, be generators of the free group on our generators. Of a free group. F4. So what's nice about Friedman's theorem is that you can construct the adjacency operator of a random regular graph directly from these permutations. So one way to state Friedman's theorem is just directly using these permutations. It's that. Okay. Let standards be the n-1 dimensional irreducible representation of Sn. If you don't want to think, like, if you don't want to understand, if you don't know what this is and you don't want to understand it and you don't want to think about it, the only reason of introducing this is because when you look at your random regular graph, you want to get rid of the eigenvalue d. Right? You always have the eigenvalue d and you want to get rid of it. This thing is getting rid of that guy. Then let rho of xi be equal to the standard representation I to sigma I, these random guys we chose. Then the norm of rho x1 plus x1 inverse, so I'm extending rho by linearity, plus xr inverse. So what is this guy? This is the adjacency operator of the random G restricted to the functions which are orthogonal to constants. So it's a fancy way of writing that. And I care about its spectral radius because I wanted both sides. Okay. But this is that's equal to 2 root d minus 1 plus small o1. So it should be 2r minus 1 here. Plus small o1. With probability tending to 1 as n tends to infinity. So this is just exactly the fact that random regular graphs have almost optimal spectral graphs. This is just a way of writing it. I want to make this is just I don't really like this because it's just a number. I did mention that it's a spectral radius of a 2r regular tree, but it's also something else. It's also the norm of this exact same element, x1 plus x1 inverse plus xr inverse, in a representation lambda, in a different representation, which makes the statement much more symmetrical. This number here is exactly this guy, where lambda is the left regular representation of the free group. So in this formulation, I'm comparing two different representations. This finite dimensional random representation and this infinite dimensional canonical representation for the group. So every infinite discrete group has this left regular representation. It's just the group acts on L2 of gamma by left translations. Right. Left regular representation. Right, and so yeah, it's an infinite dimensional representation. This is some self-adjoint. This is some infinite dimensional self-adjoint operator. It's bounded. Its spectral theory is still interesting, especially if you replace FR by some other group. We don't know about a spectrum. It's a topic of a different story. It's a different story. Okay, maybe just for today. It just so happens that you can calculate the spectrum of this operator. It's due to Keston. And it's equal to this number. Okay, so like I said, you cannot just use Friedman's theorem plus some transfer principle to get optimal spectral graph. So what are we going to do instead? We're going to ask for more than this. We want more. So how can we strengthen this statement? Tell you one way, which is not what I'm going to do. Just remove small o1. That's something you can do. Say, oh, I don't tolerate this. I'll just take it away. I want that. That's not a theorem. I'm not saying that's a theorem. But if you ask for that for a family of graphs, you get Ramanujan graphs, which we already mentioned. That's one way to strengthen this. That's not what we're going to do. We're going to do this. We're going to replace x1 plus x1 inverse plus xr plus xr inverse by any element of the group ring of the group. So this is all formal linear combinations of elements of the group. This is a formal linear combination of elements of the group. It just so happens to be the generators and their inverses. Not a very interesting one. So I'm going to ask for this for every z. But I'll just have to be careful with my quantifiers so that I don't ask for too much. Not sure if anyone will be interested in this, but both A and B are not possible. So choose one. So they're both optimal strengthenings. Any questions with this?
So A is essentially the definition of Ramanujan
Yes.
graphs.
That's what I'm saying, yeah. It's not true that random regular graphs are Ramanujan. That's numerically been observed not to be true.
Well, could you draw one
Oh,
a Ramanujan graph, an example?
it's not easy to come up with these. Like, it's hard to tell you how you construct them, but I don't know if anyone will understand it. Like, they come from quaternion algebras, and the Jacques-Langlands corresponds. So something in number theory. These are the ones of Lebowski, Phillips, and Sarnak that rely on the existence of Ramanujan graphs relies on something in number theory, which is Deline's proof of the Fay conjectures, plus Jacques-Langlands. Marcus Spielmann Srivastava construction of Ramanujan graphs is different. It's also hard to explain. Yeah. I mean, sorry, the existence of one Ramanujan graph is not the existence of one Ramanujan graph is not difficult. But if you want to have D fixed and the number of vertices going to infinity, this is the challenge. So you can take complete graph. This will work. Okay, so let's make this B more precise. What's the definition? And then coming back to Jean's question, that why we only had inputs for free groups. We want to have inputs for other groups. So now I'm making definitions for all groups. And that's and exactly your question is the impetus for me to study this. So there cannot be a discrete group. For example, the fundamental group of the surface, which is compact, or the fundamental group of a hyperbolic three manifold, or the fundamental group of any manifold that you're interested in. Okay? Proving something about the spectral gap of. Let's say we have rho I, which are finite dimensional unitary representations of gamma. These are unitary representations. Possibly, like in this case, random. Possibly not. So we're going to say that rho I, these representations converge strongly to the regular representation. And if they're random representations, we'll say this happens in probability. If for all elements of the group ring of gamma, for all formal linear combinations of elements of gamma, limit as I tends to infinity. Norm of rho I of z. Ah, yeah, I've got the right. It's equal to the norm of lambda gamma. And if we're in the randomized setting, this should hold in probability.
Lambda is left regular.
Yeah, left. I mean, the norm on the left and right regular are the same. So Friedman's theorem is the fact that this happens for Friedman's random representations and for one particular z. You're now asking this for all z. Yeah. So I didn't make this definition. It existed for me. But one definition I didn't make is, yeah, so here's the interesting thing. Given any gamma, it's very non-trivial that these guys can exist. Okay. So if such real y exist, you're going to give gamma a name, which is like in Wilhelm's talk. We have a terminology that we inherit, and it's with us for so long that we cannot get rid of it. So called gamma, purely matricial field. Okay. This comes from operator algebras, and this makes sense, but we could just call it PMF. Okay. Anyway, it's a property that says the regular representation of your group can be approximated by finite dimensional representations in a very strong way. Okay. So the first theorem really on this topic is that due to Hager-Rupp and for Bjornsson, this is proved using random matrix theory. And it's that FR is PMF. So this is 2005. So this was an open problem for like 25 years to prove this. That's good, but this is just about finite dimensional unitary representations, which aren't that useful when you're trying to do things with manifolds and graphs, right? So natural question is, can we actually just replace this element here, this linear element, by any z in this exact setting, in the Friedman setting? And the answer is yes. That's the theorem of Bordenave and Collins. And it says that Friedman's random representations, exactly the ones on that board, strongly converge to the regular representation of the free group in probability. So this is the input to my theorem of Will. When I said we work with free groups because we want to have input to come from free groups, it's this input that only existed for free groups at that point. But why does it only exist for free groups? So like, this is an interesting feature that every single, yeah, so this proof here uses random matrix theory. So does this. Every proof of everything in this area uses random matrix theory. So there are no explicit examples of anything. Like, it's yeah, I think that's one of the big questions in the area. So hang on, what was I going to say there? Right, okay. So, but why is it easy to prove things about free groups using random matrix theory? Because a random representation of a free group is just a random unitary matrix for each generator of the free group. So it's just questions about are independent, identically distributed random matrices. Okay, and this is easy. This is easier to study. But if you have a group which has some relations in it, then you have to have unitary matrices that have some relations. And it becomes much harder to randomize them. So it's not even clear what probability measure do you put on that space of, yeah. So to come back to this question, there is actually motivation for proving my result with Hyde more directly. So we now understand that there's a very general mechanism for taking statements like this for the fundamental group of a compact manifold and transferring the statement to optimal spectral gap, asymptotically optimal spectral gap. And that, I'm not going to go into that now, but that gives the impetus to try to establish this PMF property for wider classes of groups. So let me talk about that. So it's theorem 3, point with Lars Lauder. So that if gamma G is the fundamental group of a closed hyperbolic surface of genus G, to be hyperbolic, G has to be at least 2. Gamma G is PMF. And in fact, you can use representations that factor through permutation groups. This is the input that we didn't have at the start. What does this give you? Well, it gives you another proof, but it gives you something better. So let me explain what the better thing is. So you can look at all the genus G hyperbolic surfaces, right? So there's a moduli space, MG. It's the moduli space. And in my theorem with Will, we found some nice guy here, right? For G tending to infinity, right? We found a sequence of points. But there's a very nice subset of MG, which is a discrete subset, a finite subset for every G. So it's a finite subset. The arithmetic hyperbolic surfaces. So let the arithmetic guys be red. They're the ones, these guys come from number theory. So in my result with Will, we worked with non-compact hyperbolic surfaces and then we compactified. So we didn't really, okay, we ended up somewhere near the boundary actually, but we don't know exactly where we landed. And we definitely don't know how to make sure we land on one of these red guys. Now, the class of arithmetic hyperbolic surfaces is by definition closed under taking covering spaces. So if we could start with an arithmetic guy and just take covering spaces of him, then we would remain in the red set. And we could prove Booser's conjecture for arithmetic surfaces, which I think is of interest. This result does that. This proves that there's this compact arithmetic hyperbolic surfaces. G of xi tending to infinity. And on the wall.
Non-compact as well, or?
Non-compact is actually in my paper. It's actually in my paper as well, because we can start with something non-compact.
With the arithmetic ones.
Yeah, because we can start with arithmetic there. So if you want compact arithmetic, then you have to go through this. I'm actually going to linger on that point for a second. So the arithmetic guys are an interesting challenge because, like, if you work with all surfaces, right, and you find a really large spectral gap,
I mean, that's one quarter, but how do you know that those things do not have any?
I'm basically run the argument with the paper in the paper as well, but without the cusps.
No, I said, so it's the arithmetic one, closed ones.
Oh yeah, I just need to start with one guy who doesn't have a exceptional eigenvalue, and I just do it. I just, you know that Huxley has this list of, yeah, I start with one of those guys. Yeah, it just works. Like, it just so happens that it's small enough genus that it I had to make sure, I had to do Jackie Langlands as well, so. Okay, so I had to do a little bit of, there's like a page of arithmetic surfaces to just make sure that I can start somewhere nice, but I can do it. What I'm saying is that in a quite old paper, there's a list of finitely many arithmetic surfaces of low volume where there are no eigenvalues below 1/4. By that correct computation using nodal lines. Interesting paper. It has a funny title. It's called Clustermania. There's something called Clusterman sums. Right. So let's go back to dropping compact again. So, like I was saying, if you don't worry about being in this finite subset. By the way, the fact that for every G there's finitely many is a result of Borel. If you don't care about the finite subset and you find a really large eigenvalue, it's actually kind of easy to find a very small eigenvalue or even a very small eigenvalue. But making small eigenvalues is easy. Okay. Then you can just draw a line between the large eigenvalue and the small eigenvalue and you get everything in between. Okay. But if you're stuck in this like discrete, if you're stuck in this finite for every G set, then you do the same thing. So yes, you don't draw a line, but it's just, in fact, it'll be the last thing I say, I think. If you look at all the possible lambda 1 of x, such that x is arithmetic. Have a roller surface. It's a question recently popularized by Sarlacc to describe the exact structure of this set. So to describe the limit points of this set and the discrete points of this set. Okay, so there's no obvious continuity argument anymore. So what I can prove is that the limit points of this set are everything between 0 and 1. Here I can't do it with compact at the minute. So it's still not done with compact surfaces. But then I think we now have the technology to do it. So it's like not done, but it's someone could do it. And we're getting closer and closer to complete description of lambda 1s. Not quite there yet. Okay, I finish here. Thanks.